In this section on training and optimization of the Softmax classification, we shall see how to compute the partial derivatives of the loss with respect to the different parameters theta, j, k, and also apply gradient descent. Recall from binary classification that we had for the output sigmoid of the theta 0 x 0 plus theta 1 x 1 plus all this right up to theta n x n. Considering this data set made of 4 different points, we have theta, which is theta 0, theta 1, theta 2, and partial derivative of L with respect to theta, which is the partial derivative with respect to theta 0, theta 1, and then theta 2. So we combine these parameters to form one vector. We also recall that the partial derivative of the loss with respect to theta j was equals 1 over m. That's in this case 4, because we have 4 data points. That's m is the number of data points, times the sum from I equals 1 to m of xji times y I predicted minus y I target. Using this, we define the gradient descent step as theta equals theta minus alpha on m x transpose times x theta minus y. We also saw how vectorizing our solution like this permitted us to easily implement in any language. In our case, we're using the Python programming language. Now let's compare some dimensions. So we have x transpose, in this case x is 4 by 3 dimension. Actually, we have the bias term, which is this, which is not included here. So that's why we say we have 4 by 3. And x transpose is 3 by 4. Then x theta minus y, obviously x theta and y have the same dimension, so it suffices to just take the dimension of y. Now the dimension of y is 4 by 1, because we have 4 data points and each having just one column. So in this case we have 3 times 4 times 4 times 1, giving us 3 times 1, and which coincides with what we had said initially. Our next step will be to use this and finding the partial derivatives of the loss with respect to the weights or this parameters theta in the multi-class problem. So we have this multi-class problem, and then considering this data set. Now let's see that let's notice that this data set actually looks different from this one. So in this case, as usual with multi-class, we have 3 classes and more. So in this case we have this class for which tells us that we have a 1, this is a 0, this is a 2, this again is 0. Now notice that we have a 1-hot representation of the outputs. Let's understand this 1-hot representation. When you have a 1, the way this output is represented using a vector is by sending all the values or all the elements which make up that vector to 0 and taking only the points or position 1 to have the value 1. So even if we had, say, 20 classes, here we're going to have 0, 1, 0, 0, 0, 0, 0 led up to the last class. And then since here our status is 0, we put a 1 on the 0th position of our vector. So we have 1 and the rest 0. Since here is 2, we put a 1 on the 2nd position. So we have 0, 1, 2. So at this point we put a 1 and the rest is all zeros. 0, put a 1 this way. So that's exactly how we have this 1-hot representation of our output. And it's important that you understand this clearly now, as it's going to be used all through this course. So instead of predicting just a 1 or a 0 as it was in this case, now we're predicting a vector, and this vector could take any dimension. we could see that the dimension actually depends on the number of classes we're working with. In this case, we're working with 3 classes, so the dimension is 3. In the example we shall see in practical, we shall have a 26 dimension output, or a 26 dimension one hot vector. Let's move on to the parameters. We had discussed earlier that when we have 3 inputs, 3 outputs, we're gonna have 9 different parameters. And there we go. We have theta 0, 0, theta 1, 0, theta 2, 0, then theta 0, 1, theta 1, 1, theta 2, 1, theta 0, 2, theta 1, 2, theta 2, 2, which can all be seen from this schematic. We also need to note that this 0 stands for the source, and then this is a destination. So we have the source, that's the input, and then the destination, the output. So if we say, for example, 2, 1, then we're talking about source 2 and destination 1. So it is source 2, destination 1. So that's why we have the 2, 1. Then from this, each of these weights have a partial derivative with respect to the loss. So the partial derivative with respect to the loss of each of these weights can be represented in this matrix. So for this, we have this partial derivative with respect to this particular weight, and then the partial derivative with respect to this weight, and so on and so forth, right up to the end. So there we go. It is also a 3 by 3 matrix. In this case, we had a 3 by 1, yeah, 3 by 1, yeah, 3 by 3, yeah, 3 by 3. Now, if we have, say, 17 inputs, as in the case of the example we're going to work with, here we should have 17 times 26. So we're going to have a matrix which is of dimension 17 times 26. Now let's compute the partial derivative of the loss with respect to each of these weights. To find this partial derivative, we shall get the intuition from what we've done with the binary classification problem. Now in the binary classification problem, we're supposing that k, in this case, we're supposing that k is always 0, or k can be taken off because k can only have one value. So in this case where k can only have one value, it's needless put in k, because if k has only one value, then you just have to work with, you could work just with j. Now that k has, or k can take several values, we have, instead of working, or instead of having this formula, we modify it. So we still have xji as before, but then the output, we have yik instead of yi, and here yik instead of yi. So it looks like this 0, 0, 0, 1, 0, 2, which happens to be this column, is just like an instance of the binary classification problem. So this can be seen as this instance. So in this case, for one instance, we have this, this, and this, which is this instance, and then we have 1, 0, 1, 1, 1, 2, the next, and then we have 2, 0, 2, 1, 2, 2, the next, and we could apply this formula. What's interesting to note is that we shall use the same formula even with this problem. So our partial derivative with respect to the loss will have the same vectorized solution as with the binary classification problem. So in this case, we still have x transpose times x theta minus y. So if we have x transpose, we had 3 by 4 matrix as we had here, and then y is a 4 by 3 matrix. So we have here as y, we have 1, 2, 3, 4, and then we have 3 columns. So we have this matrix made of this, 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 and this. So we have this 4 by 3 matrix which we put here. Now 3 times 4 times 4 times 3 gives us a 3 by 3 matrix, and which gives us exactly what we have here. So to update theta, it suffices for us to compute x transpose times x theta minus y, as we did with the binary classification problem. If we're working with the data set we have presented earlier from the UCI website, where we had a 20,000 number of data points, and each of them having 16 different inputs. Here we have not included the bias. If we include the bias, we have 17 inputs. So here we have 16 times 20,000 since it's X transpose. And then times Y is going to give us 20,000 times 26 dimensional matrix, because each of these outputs is going to be a 26 dimensional one hot vector. And given that we have 20,000 different data points, we have 20,000 times 26. So comparing the dimensions or computing the dimensions, we have 16 times 20,000 times 20,000 times 26. So we have 16 times 26 dimensional metrics for theta and the partial derivative of the loss with respect to theta. Let us now write code to train a model which will be able to predict, given an input, whether we are dealing with a particular letter of the alphabet or not. The very first step, as usual, is preparing the dataset. When you download the dataset, what you'll get is this file, that is letter recognition.data. With this letter recognition.data file, you have this kind of information, or this is what you would have. Now, we could convert this into a CSV file. So since all these values are comma separated, we just change the extension .data to .csv, and that does the magic, and we'll have a CSV file. So this is a CSV file we'll obtain, but we have added this top row, so all these values have just been added. So if we take this, all these values were added manually, but this is the data set. From the second row downward, we have the data set. So we're going from this right up to the 20,000th value. So there we go. So we'll get back, and then we just fill this with letter to say that this is a letter of the alphabet. We have taken this. We have input 1, input 2, input 3, up to input 16. So this is a data set, and using pandas is going to be easy for us to create our inputs and outputs needed to feed the model. It's also important to note that we could work with the .data format, but that would demand much more coding as compared to just working with a CSV format and using the pandas library. So with this, we have we could define a dictionary of alphabets. We're going to see exactly why this is needed later on. For now, we have the objective, the input, and then the output. So as usual, we read the CSV file, and then we go through and create the X. I'll create the inputs and then the outputs. So we've defined X as this empty list, this. So we append 1, this is the bias. We have the row input 1, which we defined, input 2, up to input 16. And then for Y append, we just, for the output, we put in the letter, which we got from the CSV file. So now we've created X and Y. What we could do is we could comment this and then see what the output looks like. Running this, we have this error because at this level we're dealing with Y hot. So for now, let's take this off and run it. And there we go. We have X, which is 20,000 by 17 dimensional matrix. Y, which is a 20,000 by 1 dimensional matrix. So we could print out X. We could print out the first values of X, say X from 0 to 10. And there we go. We have X. So this is what X looks like. Recall that X has already been normalized, so it's nearly normalizing it again. Then we have print of Y 0 to 10, and that's it. So this is what we have. But recall that when working with a multi-class problem, the outputs actually are generally one hot coded. So instead of having T, we should say, okay, T is found with position in the alphabet. T, for example, is having the 19th value. So we need to have a one hot. Say we have this. Then we create this 0 vector, and then we come to this 26, 25, 24, 20, say no, this from 0 to 25. So it's 25, 24, 23, 22, 21, 20, 19. So this is where t is found. So at this point, or for this, instead of having this t character, we should have a vector which is one hot coded like this. So instead of that, we should have this, and then we'll go to the next, that is I. We look for i's position. I's at the 8th position. Take this, copy, send this to a 0. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, and that's it. So that's how our y is supposed to look like. That's why we need to add a section which is going to send this y into a hot notation. So now we have this hot. We uncomment this. So for I in y, that is basically we're going through all these different elements, or all these different rows. We call that we have 20,000 rows. So we're going through all these rows, and then we're generating the one hot notation, or the one hot matrix. So we have, for this I, alphabet I0. So we come back to this dictionary, and then we get this. So let's print out alphabet R0. So we could, or let's print out simply I0. Now I0 has been printed. Is basically the same values we had here, with the difference that since this array is 20,000 by one-dimensional matrix, we just want to select just this t at every point. That's why we go for this. We select the 0th index, and in this case it's t. It's true we only have one index, but since this is a list, because this is I, we're going for all I. This is the first I, this is the next I, and so on and so forth. So for this I, we need to select I0. That's I, or the 0th, the value at the 0th index of I, which in this case is t. So that's what we output here. And then we have alphabet of t. Now what's alphabet of t? Alphabet of t is 19. So we're sending the value 19 into this function generate one hot, and this is that function generate one hot. We could run it separately. We have this. We say generate one hot of, say, 19. So running this is exactly what we have. So we have this vector which has values 0 everywhere except for the 19th position, which is 1. So that's basically what this function does. So with this function, we initialize this, and then for the value we've put in, set it to 1. So it's a very simple function. Now that that's done, we can now take our y hot, convert it into an array, and then return. So basically that's how we prepare our data set. So with this, we could take off this and then rerun. After running, we have this. So instead of the 20,000 by one-dimensional matrix we had previously, now we have a 20,000 by 26-dimensional matrix. So we could print out the first values of y. So we have 0 to, say, 4. That's it. So this is exactly what we wanted. We wanted this one hot coded output. The next thing we do is define the softmax function. Now, from the softmax formula, we had a term which was like the sum, which was used at the level of the denominator. So we try to calculate the sum first. So suppose we have this as input. We could include this. We could do this. So we have 4, 5, 3. Now, for each of these rows, we want to get the softmax values. Recall that each row represents a data point, because at the level of y, we have an m by, say, 3. In this case, suppose we're having just 10 three values in the outputs, or we're classifying three different classes. So we're going to have an m by 3 value for output, or m by number of classes. So in this case, we have m equals 3. Let's take this back to 2. So we have m equals 2, and there we go. So in this case, we have a 2 by 3 dimensional matrix for y. Now for each of these values, or for each of these data points, we need to get their softmax. If we run this, we're gonna have the same value or the same answer we had in the slides. That was for this 132, which we did as an example in the slides. So we start by calculating the exponential of each of these terms, or each of these elements in this matrix. So if we take this off, and then print out the value for k simply. So if we print out k, see that we have the exponential of this. E to the power of 1 is 2.71, which is actually the value for e. So we have this for each of these values. Now what we do is we sum up these values and put it as 1, and then we sum up these other values and put it as 1, since they represent two different data points. And that's why we have the sum, and then with the axis we're working with is a negative. We're working with the axis 1, and this, or we could take it to be -1. So -1, yes, simply signifies that we're going from the right to the left. So the way you could see this is, say we print this x, print this, anyway, even printing this will give the same dimension, although different values. So if we print this, we have this value, and then selecting this axis and putting it at -1. So let's do this, that shape. So putting at -1 means we're deciding to sum it through all these three values. So that's what we're doing. So if we get a value for k, we'll have just two values, because we are summing all through three values. We're summing this, and then this, to have this 30.19. So if you add this all, you should have this 30.19. Now let's take this and run it so we could see how we have 30.19 x. Okay, so adding this up gives us 30.19. Taking this plus this gives us 11.10. That's exactly how we do that. We could also take axis 1, saying axis 1 is the same as -1 in this case, because -1 is like saying we're going from the right to the left, so we're taking the three elements. 1 again is saying we're going 0, 1, we're still taking these three elements. Now notice that if we take 0, we're going to have three different values for k. So let's take this off. See, we have three values because normally the sum is on each of the columns this time around instead of each of the rows. But since we want our sum to be on each of the rows, we have -1 or 1. So let's just leave it like that. So that's what we have. Now that we have this sum for each of the data points, we have the denominator for our formula, because our formula is e to the power of say a value I divided by the sum of e to the power of I. So we have the sum, which we've calculated already, and that's k. Then we go on. So for I in x, so for each of these data points, we want our x output to take in a new value. So we have the e to the power of I, that's for I in x. So we're taking e to the power of I. Now let's run this. We could print out print I. So for all these values, we're printing e to the power of I, or we could print out this, and there we go. So we've printed out this value for all, that's for each of the i's. We'll print this out. Now for this value, for example, That's for this very first value. Notice that after this, let's maybe do this. So you see that there's a difference. So you see there's this gap to tell you that we do this first before, for the next turn or for the next round of the for loop, we then move to this. So with this, we have this e to the power of I, which has given us this, divided by kt. Now t, as we can see here, initially 0, we move, then we keep on incrementing it, because as we saw, we had found this sum, and now this sum has two values in this case. So we are saying we are finding the sum for that particular data point, and when t is equals to 0, the sum for the 0th data point is given to us as 30.19. So we take each and every one of this value and divide by 30.19. So it comes back to what we saw in the slide. So we have this divided by this, it gives us our answer. This divided by this, it gives us our answer. This 7.38 divided by this, it gives us this answer. And then for the next data point, which is this, we have this divided by 11, gives us this, 2 divided by 11, this, and then 1 divided by 11, this. So that's how we calculate the softmax. So let's take another example to make us better understand how the categorical cross entropy loss works. We shall take this other example where we have 4 different data points. So we have the 0.8, 0, 0.2, which represents 1. So this is what the model outputs, and then this is what, or rather this is our target. And the aim is to compute the cross entropy loss for this, and then add it up to this, and this, plus this, and this, plus this, and this. That's exactly what we had in the formula, not forgetting the negative sign. So the section for a number of classes we have seen it already, but now for all the data points, basically we have to go through as we've just seen. And in terms of writing this in Python, it's quite easy, because all what we'll be doing is applying the CCE loss for each of this and then doing a sum. Coming back to our code, as we saw, we have y pred and we have y true. Now, to get the loss, we have y true times the log of y pred. So basically, if we have p and q, where we can take this to be the pred, and then this is the true or the target, which are 5 by 3 dimensional matrices, and then we could print them out. We have these matrices. Now computing y true times log of y pred will simply be element wise multiplication. So we have this times the log of this, we have this times the log of this times the log of that, so on and so forth. So let's do this. Let's print out. So we have p times np log of q. So there we go. We have this value. So we have this matrix now, which is still a 5 by 3 matrix, which is gotten by getting this times the log of this value. And then normally for each of these data points, we're supposed to do a sum. We're supposed to sum this, and then later on sum this, and now for each of the data points, we sum everything. So with this np.sum, we could simply have to sum all these different elements together and divide by m, where we could get it as the length of y pred. So in this case, we just have to do this. So we could take this off now, run this on this, and we could find CCE loss of PQ. Now, since we already had some issues because we have this negative values, which normally we wouldn't have, so we could say we do softmax of this. There we have softmax. Run it to see that we don't have this negative values again. And then now we could find this CCE loss. So there we go. We have 1.28. Now let's modify this and put this to be P. Or rather, this is Q, but then yeah, let's take this to be P. So we see that we have, if we run this, we'll be having the lowest possible values we could have. The next step, it will be to train our data set. So we have the seeding. We take X to be the first 10,000 values, because for now we're working only with the training data set. We're working only with training, so we have this. The number of epochs, we start with 100 epochs. Learning rate, we could take this to say 2. The batch size, X dot shape 0. We saw this already. In this case, we're going to be having a value 20,000. Now we have the input, the output size, the printing frequency, which we're going to see exactly why we need this. We have tether. Instead of having this as 1 as we had previously, now the output size is no more only 1. So we have, depending on our output size, like in this case we have 26, so this is going to be 17 by 26 dimensional matrix. So we have that. We have our loss. We have our best tether, because it's important to note that sometimes when doing training, you can have for, let's say we're moving from the 0 to 100 epoch. So we could suppose that at the 0th epoch we have, suppose we have a loss of say 5. At the 20th epoch we have a loss of say 0.8, and then at the 30th epoch we have a loss of 0.9, and then finally, let's suppose we're going up to 50 epochs, so we come back to a loss of say 0.85. Now what happens is we want the value of tether when we were at this level, when we had this smallest loss. So that's why we call this the best tether and the best loss. So we want to get the values, or the values of tether where we had our best loss, because sometimes during training the values of our loss fluctuates. That said, we continue with the training. Could separate this. Let's take this. We have this constants. We have this. Okay. So we have now for all values, or for, we're going through each epoch. We have epoch loss, as we have seen already, for each batch size. Now for the model output, we have the softmax of X times theta. So instead of having sigmoid as we had in the logistic regression, now we have softmax of X times theta. We have the theta, which is unchanged. Actually, we have the same X transpose times X theta. X theta in this case is still our model output, minus Y. Then we have theta, which is equals theta minus the learning rate times d theta. Epoch loss is now the CCE loss, that's categorical cross entropy loss. Then we have that if the epoch loss is less than the best loss becomes this epoch loss. So we're just trying to get the best loss and then best theta. Now our printing frequency, we're going to be printing the epoch number in which we have found. So we want to print it after a certain number of epochs. So basically that's the use of this print frequency constant. So let's run this. Immediately we see that we have a model which is divergent. So to sort this out, we could interrupt the kernel. We can now increase this. Let's take this to 4. We'll run it again. Still diverges. Then we could take this up to 5. Run it again. Find that it's now quite fine. And there we go. After our print frequency was 50. Yeah, our print frequency was 50. That's why after 50 terms we have a value of loss printed out to us. Then the loss at the end of training is the same as the loss, the same as the best loss actually. So this is our best loss and the loss at the end of the training. This is our loss function with respect to the number of epochs, and then this our value for theta. After training over 1,000 epochs, we have the results. So we'll move from 63 to 8 and finally to 1.06. So this is our theta. We modify the code to work with other optimization algorithms like momentum, RMS prop, or Adams optimization.